everybody. A quick introduction to me. I started playing with electronics and computers when I was 8. I did a degree in electronic engineering, and I've worked for the same company effectively for the last 30 years, although it's been Lucas, TRW, Lucas Verity, ZF. So I now work in the ZF Engineering Solutions part of that. I've done a lot of product development activity in the automotive industry, but about 10 years ago I started into the sort of security side of automotive, and in 2019 we started ZF's product pen testing department. So we've got about 15 people there. We've done probably nearly 90 pen tests now, and that's accelerating. We did about a third of those in the last 12 months. And recently I started a part-time PhD looking at unusual side channels, but I'm still doing work at work. And I recently joined the Security Assurance Framework group in the IoT, so I'm one of the people who was talked about as causing aggro this morning with my feedback. So today I'm going to romp pretty rapidly through a bunch of things that we've seen in recent automotive pen tests. They're all things that were in electronic control units that haven't shipped yet, so this is not stuff that's out on the road. It's had a chance to be fixed. And I think we'll find a lot of things here that are applicable to the wider IoT type of audience. So these are not things that are just to do with cars. We are the Internet of Things with wheels, but I think the Internet of Things is fine. And from that, I've got some recommendations for ways you can mitigate these kinds of things, and also how to prepare for your pen tests. So reading and writing, it's something we do quite a lot. We have a standard called XCP, the X calibration protocol. X is any kind of communications interface. And we get ECUs that come to us which have read-only access, because read-only is always fine, isn't it? So we read invalid addresses and we crash the ECU. Sometimes we can just read the flash. We can read all the keys out of the thing, which is a surprise to our customers. We had a nifty one where there was an ECU which would allow us to perform a CRC on an area of memory. So we would perform a CRC on a tiny area of memory and then do a CRC and a little bit more and a little bit more and a little bit more, and each time you can brute force what value that was. And so by the end you've read all the memory out just from doing some calculations. So don't give read-only access to people. Don't allow them to do calculations. Get rid of all the development support. If you've got to have it, then do some proper authentication, good cryptographic protocols. Another way of reading things from automotive devices, we have these things called data identifiers. They're predefined 16-bit identifiers that refer to a small or large area of memory. They might be a single byte, they might be a huge area of memory. Sometimes you can just read out the UDS key that you want to use to authenticate to it, because someone's very conveniently given you the ability to read out the EEPROM that's in the device. Even worse, sometimes you can write to the key that you're going to use, which is disappointing for them, quite fun for us. And there's also this feature of dynamically defining a data identifier. That allows you to turn a data identifier into an address. You can use that to read all the addresses with all the problems from the previous slide. So unauthorized users, be very careful what they can read. Don't let them write anything at all, is my view. People still do, and if you've got a service that provides arbitrary reading and writing, you get all the problems that we saw before. Sometimes we have constants in our system. They usually shouldn't be constant. We had an ECU that came to us which had a random number generator which was used for cryptographic purposes. When you assess that random number generator, it produces really nice results. They're very, very random. Unfortunately, they're the same every time you turn the thing on. They're the same with every instance of that ECU as well, because it was starting from 0 and then on from there. So the functional verification had been done without cycling the power to the thing, so it only saw the quality of the random numbers out of the random number generator, not the entropy that went in there. So yeah, turn your systems off and on again. And use a true random number generator if you have one. If you don't have a true random number generator, there's a paper there which I wrote which gives some guidance on using entropy you do have in your system. This thing seems to go very lively onwards. Another constant we had was a password for a debugger. So this system had a debug port. No, they didn't want to use a debug port, so they would just program a random password in and throw it away. And so they generated some random passwords, put them in there. threw them away, checked that they couldn't connect, thought everything was fine. During the pen test, we watched that process happen and realized it wasn't a random password, it was the contents of the status register. And that was the same every time on every ECU. So every ECU had the same password in it, it just wasn't all zeros. So there was no verification on the quality of the passwords. Even though they didn't care about the passwords, they still should have looked at those. This is rattling on. Yeah, when you actually do perform these kind of things, you have to look at, yes, we've locked the debug port. Have we locked it well? We have a scheme called security access, which is just a challenge and response protocol by anyone else's means, but automotive being automotive, we have to call it something different. That relies on randomness. You have to have something different every time when you send those challenges out. Otherwise, the attacker can just build up a database of things that they know the right answer to the right question. Mitigating that using something that won't repeat, a random number generator, is good. Use 8 bytes of that at least, because that gives them no chance to iterate over all of them. Give the attackers more limits in terms of you don't generate a new challenge until they've given you a response to the previous one. Otherwise, they can just keep asking until they get the right answer. When they give you a response, only let them give one response. Sometimes we get things that let you have lots of goes, and that's not good either. And then make them wait between requesting challenges and giving responses. Again, we often get things that just let us keep trying lots and lots of times. We all have software. We all need to update that software. We do that in a standard way in automotive. There's an ISO standard. This is the flow for it. The flow is very standard. You would think an ISO standard, everybody does it the same way, but everybody does it differently. So when we do a pen test, we have to rearrange all our software. We have to reverse engineer what's going on. So they're all standards compliant, but all different. That right-hand box performing the post checks, that's where you can do a signature check. We have this problem that we've seen in several systems so far, the everything is okay problem that we call it. So the attacker or the pen tester observes a legitimate download going on. They manipulate the software from that. They download that manipulated software, which has got now a bad signature now because we don't know what the good signature is. The ECU recognizes it's a bad signature, reports a failure. The code download tool puts a big red box up and says, whoa, stop in there. The process stops, everybody's happy. But there's one more message you can send at the end, which the tool has not sent because it knows everything's gone wrong. But if we send that message, it's an all is okay message. And the ECU will just believe us. And then next time it reboots, it executes our manipulated software. The functional testing was not checking the ECU's behavior, it was checking that the tool put a big red box up on the screen. So you have to look at your functional testing and make sure that the right thing is doing the rejections. Certificates, what fun. Often used in code download, but in other places as well. Sometimes we send in a certificate, just a completely random certificate, and the ECU accepts it. We don't know what it's done with it, but it didn't throw it away, which is interesting. Those certificates have to be verified against a root certificate. The ECU has to trust that certificate has come from somewhere good, but sometimes we have data write possibilities, and we can write over that certificate with our own. Sometimes we can just sign our own certificate, send that in, the ECU goes, let's check the signature. Yeah, seems to be a good signature. And it's our signature, not one that it should actually trust. Those are both easily exploitable. You generate your own certificate, sign the code, off you go. Some chips use a certificate which has to be passed in the boot process. ROM-based bootloader, bugs in your certificate parser, no way to fix those in the field. Some devices use a raw asymmetric key in those certificates. You can imagine which one has more vulnerabilities in it. So yeah, fuzz your certificate parsers, defend that root certificate you've got against changes, use one-time programmable memory, put it in HSM. Functional tests need to test that all the certificates that aren't valid are getting rejected properly. All the way from self-signed certificates or signed by an incorrect root certificate. I would personally avoid anything that's got a certificate parser in ROM. So can we boot our device securely now we've got software in it? Why do we want to do that? The attacker wants to get persistence on your system. They want to gain persistence through programming the flash. They may have already managed to bypass one of your controls. Maybe they can bypass a signature. Maybe they can execute some code transiently. The way we do it in pen testing is usually we use the debug port, so we assume someone can break the debug lock. And so we need some defense in depth. Secure boot gives us a root of trust which verifies that the code that's got in there in a good way. So in some of our ECUs, we have a hardware security module, so an isolated part of the ECU which can check what's going on at boot before we get going. It's an isolated processor. So the main application processor is not running to start with. What the attacker can do is put their own code into the empty space that's unchecked and tweak the boot configuration so that it starts their code instead. The HSM dutifully does its checks. The application hasn't changed. Everything's good. Please continue with execution. And then our code is executed. So, on to engaging with pen testers. Strangely enough, the first recommendation is to do your own testing. There's a lot of simple stuff from things I've talked about there that you can do before you send it off to your pen testers. Checking random numbers, looking at what services are available, checking somebody hasn't left in a simple bypass of if you send all zeros, it'll let you in. Keep the controls in the device functional throughout. So it's very tempting during development to leave things disabled so that you don't have to have signed code, or you can just jump past all the security access. And that often gets delivered to us as pen testers, and they say, here it is. Yeah, you haven't enabled anything. We've got nothing to test. So my suggestion is to keep all the controls fully functional, use development keys instead of production keys, and make everybody jump the hoops all the time, because that will make you test them and make them slick. When you're actually engaging in a pen test, scope it really carefully with people. Don't get them testing stuff that you know is flawed, or stuff that you don't have control over. If you have to integrate with someone who is not as secure as you want to be, don't have the pen testers tell you you need to change it, because you can't change it, unless you want that report to give to those people and say, you must change it. Don't think the pen testers will find everything. It's a sampling process. And look through all your findings. How could we have caught this earlier? Is this something we could add into this automated test suite? So, look at that security configuration, boot mode, that kind of thing. It's 1,000 pages of documentation, yes. Get it down to 50 or so requirements that everybody can implement into the product. Check the random numbers, over power cycles, over multiple instances of your ECU. Check how your software update process works. Make some inauthentic code, tweak the flow. Try and break it in simple ways. Enable the security all the way through. Have those processes running all the time. When you've got authentication protocols, you've probably got brute force opportunities. Make sure you implement all of those mitigations. Make sure the mitigations can't be turned off by just cycling the. So if you've got a 10-second timer, turn it off, turn it back on again, and the timer's been reset. And work with your pen testers. Engage with them. Do your pre-test rigorously and review the results carefully. But none of those are just for cars. I think they can apply to lots of electronic products. So take what you can from that if there's something useful. Thank you very much.